Yesterday we did Newton's first law, which is what we did the day before the exam as well. So, yeah. Okay, so we talked just briefly about Newton's second law yesterday, just kind of introduced the idea. Okay, Newton's first law obviously talks about all situations where the net force is zero. Okay, any situations where there is no net force, there is going to be no acceleration of any kind. That means either the object sits still or the object continues to travel at a constant velocity. That's Newton's first law. Newton's second law deals with all the other situations, okay, where there is a net or unbalanced force. Anytime there is a net or unbalanced force, there will be an acceleration. Okay? Newton's second law talks about the relationship between that force, that unbalanced or net force, the mass of the object, and the acceleration that that object experiences. Okay? Summed up pretty simply, okay, as F equals, or F net, sorry, equals m times a. Okay? F net equals mass times acceleration. Okay, nice easy formula to use, or so it appears. Okay, this is half of Newton's second law. Okay, when there's a net force, a mass will experience an acceleration. The other part of that is, why is there a net force? What are all the forces involved, and how are they not balanced? Okay, so there's actually like two halves to Newton's second law, and it goes more like this. Okay, yes, F net equals m times a, but it also equals the vector sum of all forces. That's the part that can make Newton's second law tricky. Okay? Obviously, I am not concerned with your mathematical abilities being challenged in any way, shape, or form by manipulating F equals m times a. Okay? That's like V equals d over t. I'm not worried about that part of it. Okay? I know that that part is the easy part. What is tricky is being able to look at a given situation or system or whatever and identify, okay, here are the forces involved. Here's the direction they're all acting and their magnitudes, because as we said yesterday, force is a vector quantity. Okay? Then put them tail to head and find the vector sum of all of those forces. Okay? Sometimes it's easy. Sometimes they're all collinear. It's like up and down or forward and backward, and the vector sum is easy. It's just positive and negative. Okay? But sometimes there are angles involved. Right? And when there are angles involved, then there's a little more to do. Okay? Again, I'm not worried about that mathematical part of it for you. Okay? What usually gives people trouble, and they take time to practice it, okay, is the identification of all the forces. Okay? Putting them together, you guys know how to do that already. All right, so we're going to go over some of that stuff and maybe get into a couple of very simple Newton's second law problems today. Okay? And then next week we're full on into, okay, that concept. All right, so Newton's second law deals with what happens when there is a net force acting on an object. Okay, again, we used the hockey puck as the example yesterday. When the player strikes a stationary puck, he causes the velocity of the puck to change because he exerts a force on it. Okay, that force is not balanced by anything else, and it results in an acceleration. Okay, how long does that acceleration last? I'm not looking for a number here, I'm looking for a description. How long will the puck accelerate for?
Until it hits something.
Okay, possibly. Possibly. It would certainly accelerate when it hits something. Okay?
As long as it's in contact with the stick.
Yeah, as long as it's in contact with the stick. The stick is what's exerting the force. As long as the force acts, the acceleration continues. Okay, once the puck leaves the stick, and we're assuming it's on a sheet of perfectly frictionless ice, okay, then it travels at a constant velocity after that. Okay, the same is true for spacecraft. Okay, when we were watching the video there where Woody floated away, okay, he could, as long as he could exert a force, he could produce acceleration. Okay, and he did. But once that force was no longer present, it was constant velocity after that. Okay, so those are the things that we need to like really understand, is that a lot of times the situation we're dealing with is only for a moment in time. Okay, and then after that, everything is balanced. Okay, the acceleration may only happen for a very short period of time, like a hockey shot. Okay, puck's not on the stick for very long. Okay, of course, as we said yesterday, the longer it's on the stick, the faster the shot. Okay, and that's where all the designs around modern sports equipment, okay, come from. In fact, it's also the design around all their safety equipment. Okay, if you don't wear a helmet, okay, in hockey, well, you can't, but like back in the day, I remember guys had hair helmets. Okay, like Craig McTavish, and he had a hair helmet. He was like the last guy ever allowed to not wear a helmet in the NHL, right? But you go back a little ways, and there were lots of guys that didn't wear helmets. There were also a lot of head injuries. Okay, now if you get a puck and you get it right in the head, okay, that force acts on a very small area of your head. Would that also be a small mass of your head? Okay. Does that mean there's a great acceleration produced at the point of impact? Skull fracture, bad concussion, okay, things like that. If you wear a helmet, okay, the puck hits the helmet and the helmet distributes that force over your whole head. Okay, is that likely to protect you from a skull fracture? Because now that force is acting on the mass of your whole head, okay, as opposed to the one small spot that the puck hits. That's the whole design, their idea around helmets, is they distribute the force over a larger mass and produce less acceleration. Okay, pads, same thing. Okay, if you're wearing a bulletproof vest, right, same idea. Bullet hits you without a vest, and it's just going to act in that one little spot. It's going to go right through you. Okay, but if you wear something hard and it can't penetrate it, it hits that and spreads that impact out. Okay, over a much larger area. You're still going to get a wicked bruise though. Okay, don't think that like wearing a bulletproof vest makes you John Wick. Okay, you're not wading through enemies and the bullets are bouncing off of you. Okay, it hurts a lot apparently. I don't know because I've never been shot, thankfully. Okay, but apparently it does hurt a lot. Okay, that's a lot of force there. Okay, big bruise knocks the wind out of you. Okay, yeah, you don't just walk around and continue to be unaffected. Right? Does that sort of make sense though? Okay, those are all things that can apply, and you're going to see so many things in this unit where Newton's second law applies. Okay? All right, so as long as the force acts, the velocity increases. Okay, now according to Newton's second law, okay, this very simple formula, if I were to double the force, what would happen to the acceleration? I used more force, but happened to the acceleration? It got bigger. It's linear. If I double the force, I double the acceleration. I probably quadrupled the force there, but I had no way to measure what I was doing. So. Okay? It's a linear relationship, right? If we manipulate this formula to solve for A, okay, if M stays the same and I double F net, A has to double. I'm dividing by the same number. All right? If I triple the force, I'm going to get triple the acceleration. It kind of makes sense. The harder you push on something, the more it's going to go. Okay. All right. Also, the net force causes the acceleration. So whatever the vector of the net force, that is also the vector of the acceleration. Okay? When I pushed on the cart went the way I pushed it. The world would be a very weird place if that was not true. Okay, by pushing something forward, it would take a hard left. Okay, that's not the way the world works. Okay, whatever direction that imbalanced or net force is acting, that is the direction of the acceleration. So that's good news. You don't have to calculate two separate vectors. Okay, once you know the vector of either the acceleration or the force, you know the vector of the other. because one causes the other. Okay, everybody good with that idea? All right. Okay, we got to talk about how we represent forces here. Okay, the little picture you see there is probably a, like a hockey puck or curling rock or something like that. Okay, but we draw these types of diagrams. These are called a free body diagram. Okay, this is kind of how we're going to represent our givens in this unit. Our free body diagram will kind of be like our givens in this unit. Okay, so this isn't a great free body diagram. Okay, I'll draw a little bit better one here. Let's say we're talking about what I did with that cart there a minute ago. Okay, so the cart is just a box. Here's the good news. In a free body diagram, everything is a box. Okay, so you don't need any artistic ability whatsoever to draw good free body diagrams. Okay, all you do is draw a box and you write the mass of the object inside the box. The mass of that cart is probably, I don't know, say 8 kilograms. Okay, so I have a mass of 8 kilograms. Now I want to identify the forces that were acting on it at the moment I pushed it. Okay, how many forces were acting on it at the moment I pushed it? Four forces. Okay, there would be the obvious force, the applied force from me. Okay, that was directed forwards. Okay, what other forces might be there?
Gravity.
Yep. What else?
Friction.
Friction. Would friction be bigger or smaller than my applied force? Well, the cart accelerated that way, right? That would have to mean that what I did was greater than friction. Okay, so. Okay, remember, these are vectors, right? The length is the magnitude, where they point is the direction. Okay, that's not changing. Force is a vector quantity. There's one force we're missing. Force from the ground. Yeah, exactly. We call that normal force. Okay, it is equal and opposite the force of gravity. Okay, so I've just identified the four forces acting on. I've represented them in my free body diagram. Okay, I've essentially got my givens there. Okay, but if I want to calculate my net force, I have to find the vector sum of those four forces. Now, this one's a little bit easier because I already know that the up force and the down force do what to each other? They cancel each other out. Okay, so I don't really even need to worry about them. It's really just these two. But if I was being like incredibly technical, okay, I would draw my vector diagram of those forces like this. Okay, this would be the force of gravity. Okay, and then I would have, I wanted purple. Okay, this would be the normal force. Okay, well, I drew them tail to head, and ooh, gosh, surprise, surprise, they cancel each other out, okay, because they were equal and opposite. Okay, and then I would have, right, my applied force. Okay, and then I would have the force of friction. Okay, so this is where I started. Okay, right here, and this is where all my vectors ended. So this line here would be my net force. Is that unnecessarily complicated for this situation? Absolutely. Okay, I would totally not do it that way. What I really have here is two collinear forces. I just take my applied force, subtract friction, and there I go. I've got my net force. Okay, what I'm illustrating here is when they're not all so easy, I still have to draw them tail to head. Okay, because I could get, a force that was directed this way, and then a force that was directed back this way. And then my net force would be the resultant of those two. And I'd have to do a little bit of vector stuff, find some x's and y's and stuff like that. Okay? All right, so the point of the free body diagram is to see the situation for what it is, identify the forces that are acting, and get them on a diagram. Then from there, you're drawing another picture, sometimes. Okay? You might be drawing a vector diagram after that, if necessary. This question, not necessary. Okay. All right, everyone got the idea of net force then? Okay, so if you were in my Science 10 class, you've seen this diagram before, okay? But this is Newton's second law in a nutshell, okay? The golfer here, he's gonna wind up and hit the golf ball in the diagram on the left, okay? He's gonna swing as hard as he can and exert the greatest amount of force he is capable of exerting with the golf club, okay? So, a reasonable sized force acting on a very, very small mass is going to produce a very, very large acceleration, okay? I mean, that much is obvious. If you hit a golf ball properly, it's going to go off. Now, for whatever reason, he decides he's going to wind up and hit that truck. Okay? Very different situation. Force is going to be the same, though. He's going to wind up and hit that truck just like he did the ball in the previous example. So force is the same, but now he's hitting an enormous mass. And that is going to produce very, very small acceleration. Okay? Usually at this point, people are like, that truck isn't going anywhere, Coder. There's no acceleration here. Okay. Still not true. It's going to look that way, right? Even if I've got the parking brake off and all of that kind of stuff, okay, if he winds up and hits that truck, I'm not saying that truck is going to roll forward or slide forward. Okay? If it was on a perfectly frictionless surface, it might. Well, it would. Okay? It would actually slide forward. Right? In the real world, that thing isn't going anywhere, right? Does that mean it doesn't accelerate? Does the whole truck have to move together to count as an acceleration? Okay? If I was standing at the front of the truck with my hand on the hood, wearing noise-canceling headphones, would I still know when he hits it? How? I'd feel the vibration through the truck. Does that mean every particle in the truck moved? That counts as an acceleration. Will there be a dent where he hits the truck? He also made that part of the truck accelerate. There's a dent there now to prove it. Okay? All of those things are still evidence of an acceleration. We simplify things a lot in this course. The truck would just go. It's on a frictionless surface, so the truck would go. Okay? And obviously that's kind of weird, but that's how we're going to do it because it simplifies things a little bit. Okay? All right, everybody okay with that? All right, so big mass, small acceleration. Small mass, big acceleration. Okay, that's the relationship. Okay, so we just talked about this here, okay, and we said that yes, net force is mass times acceleration, but it is also the vector sum of all forces, which is the part that gets forgotten, but it's probably the most important part. Okay, vector sum of forces. Okay, units. The units for force, if I multiply mass by acceleration, I am multiplying kilograms by meters per second squared, which gives me kilogram meters per second squared. We abbreviate that newtons. Okay, a kilogram meter per second squared is the unit for force, but because Newton did so much for the science of physics, he got the unit for force named after him. Okay, so a kilogram meter per second squared is also known as a Newton. Okay, you don't have to write kilogram meters per second squared, okay, on a quiz or on an exam. If you write newtons, just capital N, I'm good with that. Okay, do you still need to know what a Newton represents? You do, okay? Unit analysis is still important, okay? You need to understand what are the fundamental units of this. Just like a joule, okay? A joule is a kilogram meter squared per second squared, okay, because it's force times distance. You get another meter in there. Okay? We still need to know those fundamental units, but you don't have to write them. And you don't have to say them, because it takes a lot longer to say kilogram meter per second squared than it does Newton. Okay? Everybody all right with that? All right, so free body diagrams. There's two types of free body diagrams. I have never ever seen anyone draw one this way. Don't draw one this way. This is bad. Okay, we're not going to draw them that way. We draw free body diagrams as though the forces originate at the center of mass. Okay, you may kind of go, that sounds close to something I've heard. Center of mass sounds like center of gravity. Okay, they are the same thing, but we say center of mass in physics because it's actually more accurate. The center of gravity is, for us, the center of the Earth. Okay, that's where gravity originates from for us. All right, so we say center of mass because we're imagining that the forces are acting on the object and they're all pushing on it so that that force acts from its dead center. Okay? Is that reality for most situations? Right? Like in sports, do you talk about getting your center of gravity lower so you can be more stable? Right? Like a big, tall cube van going around a corner can roll over very easily because its center of mass is very high. Its center of inertia wants to go, okay, and roll. Okay, so center of mass is important, but we imagine everything as though it's actually entering the center. Okay, but lots of forces in reality do not. Okay, when a semi-truck tips over on the highway from high winds, right? The wind is acting all along the long side of the trailer, okay, and tipping it over. Now, are there applications of that we can think about in our real lives? Let me ask you this. You have to move. You're packing up your U-Haul, okay? Where should you put the heavy stuff? Bottom or top? Bottom, for two reasons. If you put the heavy stuff on top, it'll break the stuff underneath it. That's reason number one. That's the more obvious and logical situation. Okay? But the other thing you want is you want all the heavy stuff near the center of mass, as low as possible. If you have all the heavy stuff at the top of the trailer, when you turn, or the top of the truck, when you turn the corner, your center of mass is higher. Okay? That's going to increase the chances that you tip over. Okay? Because those forces won't be originating from the center, they'll be originating from the top. Okay? And that wouldn't be good. Right? Making sense? Okay? Like I said, we're going to talk about so many practical applications of the stuff we talk about with Newton's second law. Okay, so free body diagrams, always drawn with the forces originating from the center. Okay, and when I draw them, I don't actually make, whoa, that's terrible. Okay, I don't actually make them look like they're, if I hit it harder, it works better. Okay. I don't actually draw the forces coming out of the middle like that because I always write the mass in the center. Okay, so free body diagrams for us are going to have the mass in the middle, okay, in kilograms, and then we'll just draw the forces whichever direction they act from the outside of the box. Okay. If you have the notes package, this one's in the notes package. If you don't have the notes package, write this one down. This is going to be a pretty simple Newton's second law situation. Okay, so back in the day, if somebody's battery died or their car stalled and they had a manual transmission, okay, you could push the car and get it started. Right? You can't do that with an automatic unless you can get it going more than 30 kilometers per hour and are willing to throw it from neutral to drive. It'll make a horrible crunching sound. Okay, it's easier, much easier to do with a manual. Okay, because what would happen is you get the car rolling, and then you would put it in gear and release the clutch, and the pistons would start going. Okay, because they'd be connected to parts of the car that are now moving, and it would start compressing the fuel, which would result in ignition without using the battery, which may at that point be dead. Okay, so you could actually start it that way. Now, in this situation, we're just talking about the people pushing the car and any other forces that might be present. So let's imagine we're in a parking lot that's perfectly flat. Okay? We're pushing the car. We draw a free body diagram of that car. Okay? How many forces are acting on it? Okay? There's two people pushing. says that force of friction is also present. How many forces are we looking at? 5 forces. Person 1, person 2, friction, gravity, normal force. Do I need to draw gravity and normal force in on this diagram? I can put it on the free body diagram, but I'm certainly not going to include it in my vector diagram because I know the car's not moving vertically. Okay? If the car's not moving vertically, those two forces cancel each other out. It tells me it's on a flat surface. Okay, perfect. I know those are not important. Okay, I could put them in, sure. I can go normal force, I can go gravity, and then I can just forget about them because they cancel. Okay, mass of the car is 1,850 kilograms. Okay, so there are going to be 2 forward forces, one slightly larger than the other. Okay, we have one that's 395, okay, and we have one that is 275. Okay, and then we also have the force of friction that is opposing with 560 newtons. Okay, we want to find the acceleration of the car. So before I can find the acceleration of the car using this formula, I need the net force. Okay, I already know that normal force and gravity cancel, so I'm just going to forget that they exist for now. Okay, they're not going to be important mathematically. What do I need to do with the other 3 forces? We said F net equals m times a, and it also equals I can wait, I got all day.
Vector sum.
Vector sum of all the forces. Okay. So, since these are forward and backward, can I assign positive and negative to that? Okay, so I don't need a vector diagram here, right? It's hard to diagram collinear forces anyway. Okay, so I'm just going to go positive 395 plus positive 275 plus negative 560. That would be the vector sum. Of course, I could just go minus 560 as well. Okay, if I put all of that into my calculator, when it starts up eventually, I get 110? Yeah. Sometimes my mental math is okay. All right, so my net force is 110 newtons positive, forward in this situation. Okay, can I calculate the acceleration now? Should be able to. I know the mass of the car because they told it to me in the question. So acceleration will equal F net divided by m. That'll be 110 newtons divided by 1,850 kilograms. Okay, so kilogram meters per second squared divided by kilograms should leave me with kilogram meters per second squared, or sorry, meters per second squared. So 110 divided by 1850. Okay, is that a pretty small acceleration? It's about 6 centimeters per second squared. Okay. Now, if they push for long enough, that will start to be noticeable. Okay, just, 6 centimeters, then it's going to be 12 centimeters per second, then it'll be 18, and so on, and pretty soon the car will be rolling pretty good, as long as they got a really long parking lot. Okay. All right, so point, was it 0.59? Yeah. Okay, now write forward on that, because that's what was in the question.
Are trailing zeros significant digits?
Leading zeros are not, trailing zeros are. Yeah, that's a leading zero, so not. Yeah.
Yeah.
Okay. here's what you need to know about Newton's second law mathematically. Virtually every Newton's second law problem you do, except ones that are extraordinarily simple, will involve those two steps. Okay? You will have to find the vector sum of all forces and then use it to get the acceleration. Or you'll have the acceleration and you'll find F net, and then maybe you have to use the vector sum of all forces to find one of the forces involved. Okay? But it's basically one of those two things. Okay? But you will always have to do those two steps, just not always in the same order. Sometimes you do the vector sum first and find acceleration second. Sometimes you're given acceleration, you got to do vector sum second. Okay? But you're always going to do those two things. Sometimes that vector sum part is super easy. Oh, there's only one force here. Done. Okay? And that's the net force then by default, and you just go from there. Okay. All right. Did what we do make sense there? Right. So that one's pretty simple, right? They're all collinear, so we don't have to worry too much about any trigonometry. Okay. This one's a little bit different. This one's got some vector in it. Okay? It's actually a lot like the one you did on your vector assignment, except they're not perpendicular. All right? So in this one here, we have a 15 kilogram block, and it's on a friction-free horizontal surface, so like an air hockey table, okay, something like that. Okay, very, very, like we'll say frictionless. Okay, in the instant shown in part A, two forces, F1 and F2, are acting on the block. F1 is 35 newtons, 60 degrees from the x-axis, and F2 is 10 newtons along the x-axis. So, if I'm drawing a free body diagram of this situation, it's going to look a lot like this, except mine's going to be more thorough. Okay, I'm going to have the mass in the box. Okay, I'm going to have the first force. Okay, 60 degrees above the horizontal, okay, and it is 35 newtons. And then 10 newtons horizontally. So what's really happening here is we're looking down on this. So it's on a table and we're looking down on it. Okay. Using vector addition, stuff you already know how to do, and this, calculate for me the magnitude and direction of the acceleration of this block. Okay, so you're going to have to do some vector addition, okay, little tail to head, and then calculate for me the acceleration from that. Okay, give you a few minutes on that. Okay, anybody want more time on that one? Okay, let's have a look at this. Okay, so I've got my free body diagram. I see that those are the two forces. They don't act in the same direction, so now I need to draw them tail to head. Okay, so my vector diagram is going to go something like this. I'm going to have my 35 Newton force here. Okay, and it's going to have a triangle with a 60-degree angle in it. This will be Y, this will be X, just like we would have done in the last unit. Okay, and then I'm going to have the 10 Newton force. And you could draw them in the other or in the reverse order. You'll get the same answer. Okay? So that's going to be 10 newtons and it's horizontal. All right. That means my resultant force, or my net force, is the blue line. Okay? That is going to be the vector sum of the two forces that are acting on this box. Okay? And it's going to look like this. It's going to have an X and a Y and a theta. Okay? Except now, instead of being D, it's going to be F net. Okay? All vector quantities are added this way, right? So we've got to do a little calculating. Okay, so our X component is adjacent to the 60-degree angle. So cos of 60, okay, times 35 should be 17.5 if memory serves. Okay, newtons, and that will be east. Okay. y will be the sine of 60. That one I can't do in my head. Okay, times 35. Okay, 30.31 newtons. Oh, sorry, I said east. Am I right if I say east? Not what they said in the question. Okay. I can just say along the x-axis for now. That's about all that would be accurate here. Okay. So I'll just say positive. Okay. And then the y will be up. Okay. All right. So I've got the 35 Newton, and then for the black line, okay, well, it's just x equals 10. There's no y component for that one. Okay, so I've got to put these together. That's going to mean that blue x is going to be 17.5 plus 10. So it'll be 27.5. And blue y will be 30.31. Okay, can I calculate my net force and my angle? Okay, then that's what I should do next. Okay, so we'll have square root of that number there squared plus 27.5 squared. Okay, so there's my net force, 40.93 newtons. That's the magnitude. I still need the direction, right? It's going to be 10 to the minus 1 of 30.31, the way I have it drawn anyway, over 27.5. Okay, so the angle is going to be 47.78 degrees above the x-axis. That's all I have, okay, in this question is above the x-axis. All right, I've got my net force. What did the question want? Question wants acceleration. So can I use this formula to get it? Pretty sure I can. This is, after all, F net. Okay, they told me the mass, it's 15 kilograms. This is how pretty much, like I said, every Newton's second law question is going to go. I got to do some vector sum stuff to get the F net, and then I go back to this formula. Or I start with this formula, get F net, and find a missing force. Okay, really going to be one or the other. So all I'm going to do here is take my F net, divide it by the mass, and I'll have the acceleration. So that's going to be the 40.93, okay, divided by 15. Okay, so my acceleration to two significant digits, because 35 only has two, is going to be 2.7 meters per second squared at 48 degrees above the x-axis. Okay, did I say earlier, acceleration and net force always have the same vector. So once you find it for one, you have it for the other. Okay? Questions on that one? Okay. All right, now, lots of times with a Newton's second law question, there'll be a part B. The part B will be a step back to last unit. So using the information you still have, the acceleration, okay? See if you can do that. Okay, when the force begins acting on the block is stationary. Determine the displacement of the block after 8 seconds. Okay. Is this really just a question from Unit 1? It's an acceleration problem. Okay, we already have the acceleration. Okay, we just calculated it. Our acceleration is 2.7 meters per second squared at 48 degrees above the x-axis. Right? Okay, so doing that from memory. Just not good when you're old. Okay, so what else do I know? I know time. Time is 8 seconds. What else do I know? I know one other thing. VI. When the force acts, the block is stationary. Okay, VI is 0. All right, with those three things, can I get displacement? Okay, so we'll have that being 0. Okay, that just goes away. So 1/2 times 2.7 times 8 squared. Okay, so to 2 significant digits, my displacement will be 86 meters. What am I missing? The degrees. At 48 degrees above the x-axis. Guys, if I gave that question on a test, if I wrote forward on your kinematics test, guess what you'd forget on that question? Okay? It's amazing. It's those little things, right? Like on a final exam, that's something I would totally do. A Newton's second law question and a part B like that, and people would forget to put the vector. Okay? Just a little thing, right? But we got to remember, this is a vector quantity. This isn't, okay, for exactly that reason. Right? And guys, I don't have many tricks in my bag of tricks, and I tell you all of them. So don't get fooled. Okay? You know these are the things I'm going to do. All right, let's leave it there, guys. Good job today.